Hey, I'm Mel from New Comics. I know that this sort of scene is different from what I usually do, but this video is very personal to me for a lot of reasons. As you can tell from the thumbnail of the video, I'm going to be talking about Mr. Miracle. But what I'm mostly going to be talking about is math and the history of math. The first half of this video is going to have a very grim and somber tone because of how a lot of the history and trends behind mathematics often go undiscussed. And while I was writing the script for this video, it occurred to me that this very grim first half may reinforce in a lot of viewers the very real phenomenon of math anxiety. While a lot of people tend to only think of math anxiety as an apprehension about doing the math, I think it's important to recognize that the phenomenon also extends to a more general, tunnel vision sense of hopelessness about numbers, logic, and math in general. So if while watching the first half of this video, you feel like you need to take a break, step away, by all means. But I do encourage you to return and stick around for the latter half of the video for a more uplifting reminder that while math can be very draining at times, it can also be very liberating. And it's often during these times that math ends up being its most artistic. I hope you enjoy.
Mr. Miracle 2017, by writer Tom King and artist Mitch Gerads, is a powerful, thought-provoking book that comments on both the spectacle and the mundane, as well as a litany of other themes through the adventures of Scott Free and his wife, Big Barda. While there are a wide variety of topics I could go on to discuss with this book, I want to focus my discussion of Mr. Miracle on the infamous force of logic and nature that threatens and permeates the life of the story's titular hero, the anti-life equation. Admittedly, it's hard to have a solid discussion of the equation itself, since most writers haven't explained too much about it apart from the notion that it's a mathematical proof of the insignificance of life. However, the very concept of mathematizing the value of life is something I find worth talking about. The idea that some claims in logic, that some tinkering with numbers could invalidate a person's life, is something I believe merits discussion. To me, the anti-life equation is representative of three specific topics: the history of mathematical proofs, early philosophies on the meaning of life, and the development of Western societies to fetishize as well as simplify much of life into empirical quantities. And in a lot of ways, King's writing and Gerads' art exemplify these modern consequences of the anti-life equation. Math, as a subject, typically has the reputation of being seen as a bit of a black box for most people. In fact, when you think of math, what you probably really think of the most are calculations. Whether it's arithmetic with nebulous numbers, like 4 plus 8, or finding the area of a shape. But there's another side of mathematics that dedicates itself to justifying and providing irrefutable evidence for why the answers to these calculations or patterns are the way that they are. Throughout history, these proofs have come in a variety of shapes and styles. Some are algebraic, such as the proof that the square root of 2 is an irrational number, while others are constructive, such as the classic Pythagorean theorem. Some have been expressed as algorithmic essays, and some are even presented today as just demonstrative examples that sort of just say, See that? There's your proof.
Even between different branches of mathematics, proofs can look like very different work. Take this proof I wrote for my abstract algebra class in university. Now here's a different proof I wrote for my non-Euclidean geometry class. Despite both being mathematical proofs, they each require different types of thought processes and levels of creativity to reach their conclusions. In fact, it might be a bit more accurate to call proof making more of a puzzle instead, like Sudoku, since they both rely heavily on logic and reasoning skills.
Now, throughout the history of mathematics, proofs generally had a bit of wiggle room, where some mathematicians took small leaps in logic to justify or generalize a step in their process. I'd like to stress that this didn't invalidate their conclusions, or lead to any mistakes in their calculations either. It just felt a bit like bad manners in the math community every now and then. This all drastically changed in the 18th and 19th centuries, however, with mathematicians such as Carl Weierstrass, Bernard Bolzano, and Augustin Louis Cauchy in particular. These mathematicians are famous for having used infinitesimal values to justify much of algebra and calculus. For example, the following is known as the epsilon delta definition of a limit, popularized by the three mathematicians I've just mentioned. First, I'll show you the symbolic representation of this definition. Now, I would not expect anybody to take a glance at this sentence and immediately understand what it's trying to communicate. So, instead, this is the same definition, but verbalized. Let f be a real-valued function, defined on a subset D of the real numbers. Let C be a limit point of D, and let L be a real number. We say that the limit of f of x as x approaches C is equal to L if, for every epsilon greater than 0, there exists a delta that, for all x that are elements of D, if the absolute difference between x and C is between delta and 0, then the absolute difference between f of x and L is less than epsilon. Now, I doubt that expressing the definition into words helped make the idea all that much clearer for most people either. So, lastly, this is a far more stripped down rephrasing of the very same definition. For any graphed line, we can pick a point on the graph, let's call it A, and say it's approaching another set of points, let's call it B. If and only if moving A horizontally closer to B also moves it vertically closer to B. If we can keep moving closer horizontally, and it keeps making A get closer vertically as well, then we can call B the limit of A. So a TLDR summary of what all of this means is the very unremarkable observation of how to tell whether or not one point is headed towards another. And it's honestly really basic when I say it like that. Now, this is very clearly a hyper-rational attitude to have towards mathematics. On one hand, it was justified during its time, since these mathematicians were at the forefront of concepts that couldn't really be quantified, particularly infinity and infinite series. But on the other hand, if I see 2 points on a graph, I really don't need to check to see if they have an infinitely small gap between them in order to figure out if they're actually headed towards each other.
I bring up the frustratingly prevalent example of the epsilon delta definition of a limit because, as this overly complicated definition shows us, mathematics in the 18th and 19th centuries was being boxed into a mindset of needing to prove everything, no matter how small. The epsilon delta definition of a limit is arguably one of the most exhausting pieces of evidence of this attitude. But in real life, having to prove everything is exhausting. It's tiring and frustrating to have to justify and back up every claim and statement. And I say this as a person who enjoys studying math.
We see this facet of proof-making and mathematical defense come to life for Scott Free. in issue number 4, when Orion tries to apply the laws of logic to coax out whether or not Scott is truly loyal to the Highfather's cause, or if he's in fact under the existential influence of the anti-life equation. And I find the ending to be understandable, to say the least. It's almost dehumanizing to see something as basic as checking if two numbers are equal become overcomplicated by such a well-meaning attitude. In a way, this tone that modern mathematical proofs have really captures the essence of what Jack Kirby was going for when he first posited the anti-life equation. A style of mathematics that dehumanizes and crushes the human spirit. The mathematical fixation on needing to prove even the smallest of details brings to mind another famous mathematician, who also happened to be a philosopher on the significance and validity of life, René Descartes. Fascinatingly enough, one could argue that Descartes didn't really develop this obsession with proving minutiae until after he really began his career as a mathematician.
For Descartes, this hyperfixation on proving even the smallest of details led into his philosophy on life, leading to a skepticism and hesitancy to accept the validity of most any idea. Descartes' founding of the adequately named subject Cartesian skepticism is exemplified as a sort of personal crisis about the validity of the world around us. He raised the question about whether or not the world around him was fake. Is everything just a set of simulated sensations? Could he trust that his neighbors, family, or even the ground beneath his feet was real? Or was it all some sort of dreamlike false reality?
His solution to this problem, which you may know if you've read Mr. Miracle, is that the world isn't, in fact, a fake recreation designed to mess with Descartes. And he arrived at this conclusion with his famous line, "Cogito ergo sum." I think, therefore I am. Descartes realized he could only be sure that he himself exists, and from there he took small steps to reason that everything else must exist also.
Now, while Descartes' flavor of skepticism is still studied today, many philosophers agree that the only truly rational claim in his argument was his famous cogito ergo sum, and that the rest of his argument had noticeable holes in it. So, much like in Ouroboros of Paranoia, Descartes' skepticism, this hyperfixation on needing to use logical reasoning to justify all of life, has come full circle and led to its own ruin.
Scott Free himself monologues on how Descartes' own style of skepticism and reasoning led to other philosophers dismantling the very conclusions that he had come to in an attempt to find meaning in life. Clearly, we see this sort of skepticism and blind devotion to reasoning chip away at attempts towards finding meaningful explanations for life. And yet, this attitude Descartes had of hyperfixating on logic and reason with such scrutiny didn't go away. Now, I don't believe it's a controversial statement to say that much of Western culture and history has had a tendency to try and mathematize or quantify most anything in life. We can see casual examples of this in rating systems for products and services, such as food venues, or much stronger examples of this with a literal mathematical definition for smoothness on objects.
This sort of mentality isn't really a recent trend, especially after my discussion with Descartes. But still, some people could argue that the idea of mathematizing life dates all the way back to Greek antiquity, with Plato and his rationalization that the reason why fire caused us harm upon touching it was because it was associated with tetrahedra, and their shared sharpness was what stung our fingers.
However, I would argue that a more firm and determined attitude towards connecting mathematics to most anything in the world came more with the writings and discoveries of Galileo Galilei, who, after discovering much of the geometric and calculated orbits of the celestial bodies of our solar system, felt sure that the universe was in fact a calculated and designed world by God himself. According to Nicolas Boulot in his adequately named essay on excessive mathematization, symptoms, diagnosis, and philosophical basis for real-world knowledge, Galileo believed that mathematics was a sufficient sign of the essence of God in nature, that nature would reveal its secrets purely by geometric and algebraic deductions.
So people initially believed that mathematizing things helped us better see God's work. However, with time, this attitude shifted from God to knowledge, with a capital K instead. Philosophers in particular took up an appreciation for mathematics and the hobby of mathematizing concepts because they believed it helped them find more firm truths about the world, as we saw with Descartes.
And Western society arguably reached its peak obsession with STEMifying the world in the 19th century, when math was not only becoming more rigorous with the epsilon delta definitions, but also with the application of scientific ideas to very unscientific settings. This can be seen in endeavors to represent all of language through symbolic logic, as with Ludwig Wittgenstein. Arguably, this was very much a harmless endeavor. Wittgenstein just wanted to prove that language, this historically difficult to pin down subject that pervaded much of human history, could in fact be tamed and domesticated by rational logic. Nobody really got hurt from Wittgenstein's work here. But the same can't be said of the STEMification of a similarly difficult to pin down subject of everyday human life: society. The 19th century saw the rise of STEM-ish programs, and thought processes that sought to actively influence the structure and well-being of society in much of the Western world. This was the era of IQ tests, which, regardless of your stance on these exams nowadays, it's unavoidable to ignore the fact that these preliminary tests were hugely biased in favor of the white upper class. The faith and insistence in the validity of these exams, because of their logical, scientific, and mathematical foundation, was used to justify employment gatekeeping, tracking in public schools, and even the restriction of the reproductive rights of individuals. A far worse example of how, quote-unquote, science was horribly misapplied to societal settings was the popularity of social Darwinism, the perversion of Charles Darwin's theory of natural selection, the belief that creatures who were most fit for their environment thrived and conquered in their setting. Social Darwinism was adopted and preached by Western societies to both retroactively justify race-based atrocities, such as slavery and conquest, as well as to reinforce discrimination, inhumane treatment, and bigoted attitudes.
Now, I'm not bringing up these atrocities performed in the name of reason for nothing. In fact, this is a pretty cursory survey of just two from a myriad of examples of how blind devotion to rationalist subjects have cruelly harmed humanity. In Latin America alone, this entire era of misapplying the sciences to human life and society is infamously known as the era of positivism, an era where thousands of people believed they could justify injustice just because they thought it was empirically possible to do so.
Reading Mr. Miracle and seeing Scott Free feel trapped and gaslit by a mathematical formula that claims to justify the insignificance of his life, I can't not be reminded of how this has historically been building up for much of the world.
Now, I've spent a lot of time talking about the real-life facets of the anti-life equation, how its nature as a mathematical proof blends almost a little too well with the fact that modern proofs tend to be dehumanizing and overly complicated. How its conclusion that life is meaningless falls in line with some philosophical beliefs on the issue, and how its very existence as a mathematization of the very concept of human life has already been characterized in the attitudes and actions of much of the Western world.
But what does this all mean for Scott Free? Well, we clearly see Scott and Barta overcome the physical conflicts that stand in their way. And yet they never quite overcome the anti-life equation itself. They can't. Not really. But they still find a sort of happy ending, despite that.
So, I'd like to go through these lenses of mathematics and philosophy again, but this time continuing on from the 19th century and into the 20th century to show how they tie very well with some of the final words of our protagonist by the end of the series.
In a lot of ways, geometry as a subject laid the framework and foundation for what Western mathematics was to be like. Under the Greek mathematician Euclid, geometry presented math as just a handful of simple rules, and showed that you could build on them and create a tapestry of logic and reasoning with understandable theorems and conclusions. Now, these simple rules that Euclid started out with were really basic stuff. There were only 5 of them, and for the most part, they expressed basic ideas like you can connect any 2 points with a straight line, or all right angles are equal. These rules were called postulates, and Euclid only had 5 of them. But his 5th one seemed to really stand out compared to the other simple ones I've just named. I've put up the 5th postulate in its original wording, and this explanation definitely isn't as intuitive as the idea that you can make a line if you connect 2 points. So, here's a more stripped down explanation of what it's saying. Let's say you have 2 lines crossing a 3rd line. Now, we look at the inner angles that our first 2 lines have. If their angles don't add up to 180 degrees, then these lines will eventually cross each other if we draw them out long enough. In the math community, this postulate is known as the parallel postulate, because if we get that special case where the inner angles add up to exactly 180 degrees, then the lines are parallel.
Now, unlike Cauchy, who wouldn't come until over a millennium later, Euclid wasn't trying to overcomplicate such a basic idea. This was genuinely his best attempt at trying to explain how you get parallel lines. However, that didn't stop a long line of mathematicians throughout history from trying to take a swing at the parallel postulate and try to prove why it's true.
There's this classic approach towards proof-making called reductio ad absurdum, where you prove one idea is true by assuming it's false and showing that you reach an obvious contradiction in logic. One Russian mathematician by the name of Nikolai Lobachevsky sort of followed this approach to try and prove the parallel postulate. But he couldn't find a contradiction. He followed the rules of Euclid's geometry with just one slight difference, and instead of finding errors and paradoxes, he found a brand new way of understanding the world. He had discovered hyperbolic geometry. I can't stress how groundbreaking it was for humanity to discover hyperbolic geometry. Before its discovery, one of the classic reasons for appreciating Euclid's geometry was because it seemed to be the branch of mathematics that brought us closer to the design of the universe, when astronomers like Kepler and Galileo found just how precisely and geometrically calculated the orbits of celestial bodies were. Euclid's geometry honestly felt like the framework for understanding reality. And so when mathematicians learned that tweaking Euclid's rules into looking like an obvious mistake only led to a consistent and equally logical way of exploring geometry, it was revolutionary.
One of the biggest changes that came with this revolution was a shift in attitudes towards logic and proofs. Before, conclusions in mathematics were only considered logical if they seemed true. That is, they could be represented in the real world, which led to resistance towards mathematical ideas such as negative numbers, imaginary numbers, and infinity. But conclusions after the discovery of hyperbolic geometry were considered logical if they were consistent. That is, if they followed their own rules. Mathematics wasn't this absolutist decider of unquestionable truth anymore, like philosophers and mathematicians had hoped. There wasn't one undeniable answer for all of reality anymore. It was possible, and even okay, to get different answers, so long as they were consistent.
Bringing the conversation back to Scott Free, this discussion on the logical consequences of hyperbolic geometry feels very applicable to Scott's realization that the world he's living in isn't the only one. Given the choice between the world of heroes and crises that we're familiar with, and the world that Scott's known these past few years, we see him choose his newly familiar reality rather than the one he's quote-unquote supposed to be in. His decision feels comparable to the decision that the math community had towards accepting or rejecting the rationality of hyperbolic geometry. Other characters act like there's only one true answer to the decision, like how some mathematicians genuinely believed Euclid's geometry was the only true way of understanding geometry. But, like we see Oberon mention, both worlds and both geometries are equally valid and real. And Scott seems happier for it. Scott's attitude in the final chapter of Mr. Miracle has a noticeably chipper tone compared to his life prior. Whereas before he'd fall into paranoia and guilt over whether or not his life was truly worth living, the final issue sees him very much happy and content, even despite the haunting reminders of his past and the anti-life equation itself. He's so jovial, and yet we can't really say he's feigning ignorance either, since he shows himself to be keenly aware of the gravity of his situation.
The way we see Scott Free smiling, despite the crushing weight of the anti-life equation, brings to mind the philosophies of two 20th century Frenchmen, Jean-Paul Sartre's philosophy of existentialism and Albert Camus' philosophy of absurdism. For some of you, these subjects may be familiar after having watched my videos explaining and analyzing these philosophies of life with characters like Spider-Gwen and Batman. I go more in-depth on these two branches of philosophies in my other videos, so I'd recommend you check those out if you want to learn more about these topics. But for now, I'll give a cursory explanation of these ideas.
Both philosophers believe that life didn't necessarily have any innate meaning. However, they go about different styles of reasoning to see why we don't have to fall into crisis over this lack of meaning. For Sartre, he believed we had to construct our own meaning. He believed that each individual had to figure out for themselves what would make their lives meaningful and pursue it on their own. For Scott Free, the existential growth from despair can be seen in the way he upholds his family above all else. He finds his personal meaning in life by way of his wife, Barda, and his son, Jacob. Meanwhile, for Camus, his emphasis on the absurd, the insurmountable disconnect between people searching for meaning and an apathetic universe, kind of throws the idea of meaningful life out the window. However, what Camus shows us, by upholding the image of the Greek tragedy of Sisyphus, is that meaninglessness doesn't rob us of our capacity for happiness. Camus encouraged that we find our own form of internal rebellion against the uncaring nature of reality, by finding ways to be happy in spite of despair. And again, we see scenes where Scott adopts this absurdist mentality, instead of flinching or falling to the idea that the life he's living doesn't necessarily matter, he goes about his life happy and confident in himself. He's achieved a sort of self-actualization because of it.
If there's anything I took away from the adventures and personal conflicts of Scott Free in his story, it's that it's important to remind ourselves not to have such a tunnel vision perspective on the world. Just because one thing is true doesn't invalidate or falsify everything else. I feel this is captured best by the ending of Scott's story.
The final page of the final chapter of Mr. Miracle bears these two panels, where Barda ominously utters a phrase that has thematically been associated with the cruelly mathematical anti-life equation. Darkseid is. And Scott, instead of trying to prove her wrong, or spiraling into crisis over hearing her say these words, reaches his own personal conclusion that doesn't invalidate hers, and says,
"Yeah, I know. But we are too."